Okay, so I found this problem from 2018, year before last test. And I wanted to work through this with you because it has lots of good questions. It's a good question. And it's important that you sort of put these ideas together and come at it from a different direction. And, okay, so N2O3 reacts with water to form nitrous acid, a compound involved in the production of acid rain. The reaction is represented below. The skeletal structure for HNO2 molecule is shown in the box. Complete the Lewis dot diagram for the HNO2 molecule, including any lone pairs. Okay, so we've got to figure out how many valence electrons we have. Oxygen, we have 2 of them. They're each bringing 6, so that's 12. Nitrogen, we have 1. It's bringing 5. And we have 1 hydrogen. So we're going to be using 18 electrons. Yes, you have to count every time because you don't know when double bonds are going to be there or anything like that. So we have to hook them together. So we've used 2, 4, 6, 8. So I've hung my outers. Now I'm going to fill my outers. So that oxygen has 8. This oxygen has 8. You notice that that nitrogen is the central atom because it's the least electronegative. So now I've got, that's 8, and 8 is 16. I have 2 left, so I put them on the nitrogen. But now I have to double check. Does nitrogen have 8 electrons? No, it has 2, 4, 6. So remember, everybody gets 8 electrons, and so I'm going to slide and share. And I'm not going to take from the one that has the hydrogen on it because you'll learn soon enough why. But it just seems a little more sensical that we do it over here. So then I'm going to slide and shift. So I slide that pair around and I shift these so that I have 3 separate areas of electron density. And there you have it. Okay. All right, so just backtracking. Everybody gets 8 electrons. That's 4 bonds. Or somehow or other, whether it's shared pairs or lone pairs. Everybody gets 8 except for hydrogen. And it's going to be satisfied with 2. So an oddball is beryllium, satisfied with 4, and boron satisfied with 6, and anybody in period 3 or above can actually have an expanded octet where they can hold more. So if you did all this and everybody was satisfied, and you had extra electrons, you just plop it on the central atom. Okay, all right, so next question. Based on your completed diagram, identify the hybridization of the nitrogen atom in HNO3. So how many areas of electron density do we have? We have 1, 2, 3. So hybridization means how many of your orbitals are you smashing together? We need 3. S is 1. P, I need 2 P's because we only get 1 S. So sp2. 3 areas of electron density, 3 little rooms, 1 for the S and 2 P's. All right. Then the question says, you see how they're putting bonding right here in the middle of an acid-base question? Oops. Okay, so I've got to erase this because I'm not on my real board. All right, so the next question says, the next part of the question says, to produce the aqueous solution, the student bubbles. To produce an aqueous solution of this acid, the student bubbles this N2O3 gas into distilled water. Assume the reaction goes to completion. That means single arrow, like that. And the only thing you make is HNO2. Okay, so that's not the reaction. Assume that you are making, it may have been up here, but assume you're only making that. To determine the concentration of this acid, this nitrous acid, a student titrates a 100 milliliter sample of the solution. Of what solution? That acid solution they were just talking about. Grammar matters. With 0.1 molar KOH. The neutralization reaction is represented below. One of the things they like to have you do is to write that net ionic equation, so you need to remember that only your strong acids and strong bases and soluble salts get written as ions. All right, so I have to keep erasing. Sorry. All right, so we're going to titrate adding a strong base. Here we have a weak acid in our beaker, and it said we had 100 milliliters of this. So that's 0.1 liters. This is our weak acid HA. Always just a good general representation. We're going to be dropping in OH minus. What molarity? 0.11. 0.100 molarity. Okay, so here's the neutralization reaction. All right, so what am I going to notice first? First, I'm going to notice that this equivalence point happens at 20 milliliters. And this is about my halfway point. It's above. So that's going to be my equivalence point. I've got a weak acid, right? A weak acid, so I'm always going to be worried about that half equivalence point. That's where half of it, when you're halfway to the neutralization. Because at the half equivalence point, the pH is equal to the pKa. And very importantly, however much weak acid you started off with, that is the concentration of the anion. Okay, so remember when you started here, all you had was HA, okay? As you added the hydroxide, you started producing this A minus. When you get here, by the time you add half of it, these two things are equal. On the other side of it, you're converting more of the HA, and so the HA goes down, and what comes up? A minus. Until you get here and you have no more HA, it's gone. And what do you have left? A minus. That's all that's floating around, because all of your OHs have matched up with all of your H pluses and made water. So that's why we say, remember, this is like our salt. That's why at the equivalence point, the salt determines your pH, because that's what you have left in your beaker is A minus. After you pass this point, now what are you adding? You're increasing here OH minus, and A minus is going to get to a point where it's just consistent. It's going to be constant. Okay, now, something else I want to point out. And I sincerely hope you're paying attention. I've not answered a single question. I'm not looking at the questions right now. Remember, we call this the buffering area. You are buffering your way up to this. This is also a buffering area. Okay. But we're not going to worry about that. Nobody's going to really ask you about that, I don't think. Okay. But now this is buffering. Remember in here, okay. Remember when we did the walkthrough and we started off and we had the pH was only due to, the pH of the solution was only due to, when we did weak and strong, it was only due to the weak acid. Then, as we added OH minus, remember we had to go to war in Mole Town, right? Because we had an invasion, just like this. This is all an invasion. Every one of these invasions, but you remember that just when we added a little bit, we would end up with some of, I hope you remember this, we would have A minus and water, and we didn't really care about the water. Remember this? And so then we would say we added, I don't know, whatever. This was a constant. Let's say it started off at 2 moles, and I added 0.01 moles. Well, remember this one, we have to, who's the limiting? take away the least, so that one got all used up, minus 0.01. And then we had to add this. Whatever was used, we had to add it over here. So it lost that. This one lost that. This one gained it. Okay, so we had, what do we have left in our solution? 0.01 and 0.01. Okay, let's see if I can just get back over here and not do this. Oh, dang, what happened? It went away. Okay, so I can't do it. All right, so what I had left here was 0.01 of this, 0.01 of this. And so what did we call this when we had a weak acid and its conjugate base? That was a buffer, right? Okay. Now, every single time you add strong to weak, when you mix that together, you are making a buffer. Why am I telling you this? Because you did it over and over and over again. If you go back and you look at that, where we did the initial titration problem, where we just kept adding a little bit more, calculating the pH, adding a little more, calculating pH, and we were continually seeing that this was a series of invasions. So titrations are often a series of invasions. But as soon as strong hits weak, you are making yourself a buffer. Okay, that is. Because you're going to be adding whatever the weak is missing. So if you're adding H plus to NH3, when you add this together, you're still going to have some of this, right? You've got your weak, but all of a sudden you're creating the counterpart for the buffer, a weak base and its conjugate acid. Okay, so, or if you had OH minus and you're adding it to HAC, acetic acid, as soon as you do that, you're creating that AC minus, the acetate ion. So, here's the story. When you want to make a buffer, you add weak to strong. Okay? Or strong to weak, whichever. You mix those two things together. There was a lab that you typically do that you didn't do. And so it is much to your advantage if you pay attention to what I'm telling you right now, because you missed out on a considerable bit of learning not doing that lab. Okay? Now, I want to say, before we even answer the questions, I'm not talking about the questions yet. So on the titration curve, we call this the buffering zone because you are continuously making a buffer, 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 buffer. And then remember when we got to the equivalence point, and when you had both of these were at the equivalence point, the moles of base equal the moles of acid. And so these were both out. And what did you have left over? A minus. And then what would you do to find the pH of it? You would take that. It's a salt. You're going to throw it in water. Do hydrolysis. All right? And so you're going to react it with water. It's going to split the water. Transfer of hydrogen. Okay. So that's why this is called a buffering region. And we're going to talk. I need to talk to you about buffer. I need to go over some other things with you, but I'm going to save that for the moment. But I hope you paid close attention to that part. So I'm going to make myself a note over here, and you can ask me if I forget. So I want to talk about effective buffers again. How would you make an effective buffer? I need to talk about buffering capacity. What does that mean? And then I also want you to think about this. It doesn't matter if you drip things into one another, because when you were going to make a buffer in the lab, you were going to take this beaker of stuff and you're going to measure the graduated cylinder. You were going to put it in here, and then you were going to take from the reagent bottle, and you were going to put so much of this, and then you're going to dump one beaker, whatever your measured amount was, you're going to dump them together in a beaker. So you're making your buffer by dumping things like a strong acid into a weak base. Or because you would take a salt and you would dissolve it like ammonium chloride, and you would dissolve that to get yourself this part of your solution. Okay, we're not going to worry about the chlorine. It's just going to be floating around in there. So when you dissolve that in your beaker, this is what you really had floating around in there. Okay, so how could you make a buffer out of that? Well, you could add ammonia, right? So if you add the right concentration of ammonia, you could add ammonia. So now you've got a weak base and its conjugate acid in the same beaker. You got a buffer. You could also, if you were looking at, now this would be if you wanted, you would want a buffer with you would want a basic buffer, right? But if you wanted, but even if you have this, what would it look like if we had a buffer solution and we dumped a strong acid in it? What would that look like? That's called an invasion. Now, let's think about this. If I have in here HAC and AC minus, let's pretend that's our buffer. Which one of these is this thing going to react with? I sincerely hope that you said the AC. Oh, goodness, what was that? The AC minus, because this is HAC. That's an acid. Has no attraction for that hydrogen ion. But this sure does. Okay, so that would be like an invasion problem. Okay, so if you wanted to make a buffer, typically what you would do is add strong to weak. Okay, that's one common way to do it. Okay. All right, and you could see that that's exactly how it worked out in our titrations. Okay, now, back to the question. I'm not going to clear it all. I'm just going to erase. Okay, let's go to the questions. E says, determine the initial concentration of the H2. This what they mean is determine the concentration of the HNO2. So it's not go look at the pH and find out the hydrogen. That's not what they're talking about. Anytime you're finding the unknown concentration, it's always the initial. I mean, that would not make any sense. And so we have, this is where we're going to use our, so how do we find the concentration of what we're looking for? Of the unknown. Molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. And so here, okay, let me give you a little warning that you have to put all your units and your substances in, just like you were doing an all-out stoic problem. And so you're going to say that HNO3 molarity is equal to the molarity of the base, which is 0.1 mole per liter, and I'm just putting OH minus, times, I gotta go to yellow, the volume, which is 0, at the, what volume? The equivalence point, because where does this happen? At the equivalence point. And they gave it to us. The equivalence point happened when we added 20 milliliters. So 0.2 liters. That's key in on that. Always. Very important. And then we're going to divide that by how many milliliters of the acid did we have? 100 milliliter sample. So we've got 0.1. We've got 0.1 liters of, we can just call it HA. I don't know what that's supposed to be, a 1. Okay, I didn't put this unit over here, dang it. So I should put liters of OH minus. And somewhere in here, because they always want to know that you know, there is a 1-to-1 molar ratio between the HNO2 and OH minus. They always want to know that you know that. So you just throw that in there when you're going to do, if ever you're going to use MAVA equals MBV, you always put that in there. Okay, and so doing a little handy dandy math, I say 1 times 2 is 2, but I've got 2 decimal places, so that's 0.02, so 1, 2, and I'm dividing it by 0.1, so that's another 1 over. So that's going to give me, I get to move it back 1 over, and so that is 0.2 moles per liter of the HNO2. Did y'all see that? It's kind of ugly. Sorry. Okay. Estimate the pKa for HNO2. pKa. Okay, what do I know about pKa? Right here. Oh, look, I erased part of it. At the half equivalence point, pH is equal to pKa. So at the half equivalence, so what's my half equivalence? 10. 20 got it to equivalence, half of that is 10. So here, you've got to go really try to be as accurate as possible. I'm going to erase this so we can see better. So if you zoom in, here is 10. Where does 10 meet the graph? Right here. Okay. I'm looking, and what I see is that this line is 4. That's 4. This line is 3. So it's not quite, so half of that is 3.5. It didn't make it to 3.5, but it's very close. So I'm going to call that 3.4. 3.4. So pH is equal to pKa at that half equivalence point. So don't forget that. Okay, that's important. All right. Next. Okay. During the titration, after a volume of 15 milliliters have been added, so here I am, 15 milliliters have been added, which species, HNO2 or NO2 minus, is present in a higher concentration in the solution? Justify your answer. Okay, right here at this half equivalence point, HA is equal to A minus. Those are equal right here. But now they've gone on and added this, so what's happening? Am I getting more HA? No, I'm tearing that stuff apart as I drop in my OH minus. So as we add more OH minus, HA decreases, this increases, remember, up to the point where that's all you got left in your solution at equivalence point. So what's my A minus? It's this one. So NO2 minus, since uh, 15 milliliters is past, well, the half equivalence point, that doesn't sound right. shouldn't say past. The equivalence point more NO2 is present. I'm not sure if we should insert past or beyond. I don't guess it matters. You could say 15 milliliters is more OH minus than is required, is more than the amount required to reach the half equivalence point. Therefore, more NO2 minus is present. Okay. All right, so I think that was a very good question. Let's go see the points. Let's go see what we got. All right, so looked at them, draw particular diagrams. Okay, so how many points did we get for our? One point for a valid diagram. SP2, another point. Racking them up. Okay, 1 point is earned for the correct calculation of the concentration, 0.02 molars. Oh, what did we do? I did the math wrong. Should have got that calculator. 0.1. Oh, jeepers creepers. I put there's 200. Look at me. Don't be me. See, this is what happens when you do trashy work. That was all some ugliness. And look, I'd have missed my whole point because of the 20 mils. Dang it. That's a lot of work to miss that point. That is 20 mils. Dang it. All right, what do we got next? The pKa is about 3.4, so you would have gotten credit for something above or below that. But we got it, so you remember what I did when I went and said, where's halfway and how close was I to halfway? Okay, so here's the answer for the equivalence point in AOH. So that's a point. 1 point is earned for the correct choice and a valid justification. So you had to get it all to get the point. So that was correct. Titration. Oh, look, they used the word past. Half equivalence point. Therefore, there will be more conjugate base present, and that is what we said in O2. Okay. All right, so we got that point. Well, we lost a point because I can't write 20 milliliters is equal to 0.02 liters. Okay, all right, so I hope you watched this. I hope that was helpful. And I have some other tidbits to tell you before your big test tomorrow. And, yeah, so I'll be back shortly.